Hi everyone, welcome back to another amazing episode of today's podcast, and thank you so much for tuning in. Today we are blessed to have on one of the world's arguably best researcher on anti-aging, Aubrey De Grey. And if you don't know who he is, he's the Chief Science Officer for SENS Research Foundation. You can go onto SENS website, sens.org, to find out what they do and donate to the cause that they are fighting for. It's quite actually amazing and revolutionary, all of the science and the studies and the research that they are doing. And we tick off and go through and basically touch the iceberg for some of all the things that Aubrey's currently working on, and it's quite fantastic to see. We also talk about the $25 million cryptocurrency investment that has happened in SENS research, and also just taking a note that it still isn't enough at all because the work that they're doing is so it's so amazing. Words can't describe. What Aubrey does is what he's best known for is some of his books and featuring on Joe Rogan's podcast. That is also where I found him, and I understand where anything that I know about anti-aging comes from him in that podcast. So essentially, he's written like a few books, one of them being The Mitochondrial-Free Radical Theory of Aging, and also Ending Aging, the rejuvenation breakthroughs that could reverse human aging in our lifetime. And I'm just so excited to have Aubrey on this podcast, and I hope you guys enjoy it as much as I did. He's just come out from the past few days of finding out about this investment into SENS, and he's overwhelmed and ecstatic with it. Today we get in not just to the science, we do get into some of the human side of things as well, and it's quite touching some parts of the podcast, and I'm really quite proud that Aubrey come on and got to share some of that, like that side of himself, in terms of the hard work that he's doing, the hard work that his team's doing, and what they're actually coming and the challenges that they're going through. It is beautiful to see. So without further ado, just to let you guys know quickly, is that Eternum Labs, if you guys don't know, have two new products out at the moment, one called Zen and one called Zone. Basically, they are awesome, perfect blends that have, Zen is a perfect blend for sleep, Zone is the perfect blend that has all the juice and gas to your brain to help your brain work as effectively and efficiently as possible without any stims. So you don't need caffeine, you don't need anything else. It just helps you get in the zone, get into a flow, and get going. The Zen helps you get rejuvenational sleep, getting better dreaming sleep and better deep and restful sleep, which is quite amazing. Also, if you guys don't know, I spend a lot of time researching and cooking and prepping highly nutritious food. And what I have done with all the food that I've been eating and using for training, health, longevity, all the different benefits for the past, I'd say 8 years, I have condensed and put into a recipe ebook that is linked in the show notes below. Also, if you'd like to get in contact with Aubrey or understand anything that is happening with the SENS research, please just look down the links below and you'll be able to find everything you need to in regards to what he is doing. It's just, I don't have the words to express how fantastic it is. So without any further ado, guys, I hope you enjoy this uninterrupted podcast with Dr. Aubrey De Grey and get to enjoy this fascinating, amazing, overwhelming conversation. So thank you guys so much for listening again. And if you do find any benefit out of this podcast, please like the podcast, please subscribe to the podcast, please rate and leave a review, especially on Apple Podcasts. Like, that helps us as the podcast out so much, and it helps reach it to other people, which is quite fantastic. And if you wouldn't mind, if you got any value out of any of these podcasts, please share it on your story. You can just go down, click copy link really quickly. Even if you like right now, you can pause the video right now, pause, click copy link, share in your story. Listening to this, guys, super excited. That would absolutely make our days. Thank you so much for tuning in, and we will see you in the next one. Enjoy this podcast, and I hope you enjoy it as much as I did.
Yeah, so this guy Richard Hart, who's been a fan of ours for like 15 years, volunteered at a couple of my conferences like 10 or 15 years ago, not heard from him for literally, I'm going to say, nearly a decade.
Yeah.
Suddenly he comes along and says, right, I've decided now's the right time for me to help you. But he doesn't do what other people like, Vitalik Buterin have done. Yeah. He doesn't come and say, like, here's a check. He says, right, what I'm going to do is I'm going to incentivize other people to send you money. And he's got a lot of other people. Richard Hart seems to be. I mean, I don't understand the crypto world at all. Okay, though they
Me,
very much seem to understand me. We have a huge fan base in the crypto community.
yep.
Um, but yeah, I mean, so Richard, you know, I had no idea what he'd been doing. He seems to be a rather polarizing figure. There seem to be people who really disapprove of him, but honestly, I don't quite care right now because he's, you know, he's done this enormous thing for us. And actually, to be perfectly honest, I'm not even sure that the disapproval is all that deep, because I wrote to Vitalik Buterin, the guy who created Ethereum and who has been a huge supporter of ours for a few years now, and told him what was going on. And he said, "Oh, that's very interesting. I mean, you know, Richard has been, you know, marketing his currency in a questionable way. I don't know any of the details, right? Um, but this, I mean, his words were, this definitely improves my opinion of Richard. And if it's good enough for Vitalik, it's good enough for anybody, right? So yeah, so basically what's happening is is Richard got his extraordinarily devoted and, as far as I can tell, very large following of crypto enthusiasts to give us money in return for a kind of quasi promise. It's not a contractual promise, because if it were, then
immortal.
yeah, I mean, the important thing is actually it's not contractual, so that's actually quite important, because if it were, that would impact the tax benefits. Um, but Richard is implying, kind of semi-promising, that if somebody gives us money, then they get a certain amount of his new cryptocurrency called Pulse for free. And of course, nobody has the faintest idea what that currency is going to be worth, you know, 10 minutes from now, let alone 10 years from now. But that seems to be enough to get people to be giving us a ridiculous amount. It's like, and the thing is the way it's been arranged is really good, because it directly, you know, connects us with this whole new community. Literally 99% or more of the people who are donating to us through this, what he's calling the airdrop, are new donors who've never been in our circle before, right? So this means we have, and some of them are, a huge proportion of these people are donating really respectable amounts. The top donor gave us literally $10 million. But we've had a couple of 7-digit, you know, at least half a dozen 6-digit, you know, dozens and dozens of 5-digit donations. So you know, it's like we're up at we must have crossed 25 million at this point, and we're only 4 days in, 5 days in.
Because when I read this, I read it yesterday, because obviously we had to change the podcast time. And when I read that, I was like, "What? Like, what is going on?" And so your mind would just be like, "What do I even do at the moment?"
Well, I mean, of course, the main thing is right now is, the way that this thing has been arranged is that we do a lot of the work. We at SENS, we connect with the donors, we verify the donations, because of course a crypto transaction is anonymous, and so in order for it to be identified with a particular person, there has to be some parallel step that verifies it. So we're doing all of that, and the result is, we're just getting no sleep at all. The heroism of the team that I have working for me, and I'm not getting much sleep, but there's 3 people who are really the point people for this. It would be more. It would be the entire team, except that there's a lot of technical trickiness in it, a big learning curve. So these 3 people are just getting no sleep, and you know, it's like, my team. One thing the thing I would say that I am the most proud of what I've achieved over the past 20 years is nucleating such an extraordinarily committed band of, crusaders. And I've always known and been immensely proud of that. But what I'm seeing from my team right now, it just beggars belief how dedicated they are.
Well, good on you. You guys are it's deserved, you guys are trying really hard. You've been doing phenomenal work in general, and you've cultivated obviously the team yourself, and they look up to you and you look up to them, and you're working really well together, and yeah, massive respect for that. I'm sure you could be so
Actually,
proud.
you put it exactly right, because people come up to me in the street all the time and thank me and congratulate me for my work. It's quite easy to maintain a certain level of self-esteem and and drive and everything when that's happening. But my team, my foot soldiers, don't get that. And despite the fact that they don't get that, they still work every bit as hard as me. They're just as dedicated, so I really look up to them.
Yeah, I get that. And that would motivate you to do better. And then you just go in this big motivation circle helping each other out. And now you don't even need sleep.
I wish. One day.
Yeah, very true. So what are you working on currently?
Well, of course, as you know, SENS is by definition a divide and conquer strategy. It's a strategy that involves characterizing the many different types of damage that accumulate in the body and fixing them all. And the problem is that any one of them can kill you on its own, more or less on schedule, however well you fix all the others. So we never want to just work on one thing or even a couple of things. The way we prioritize stuff is simply by looking out for and paying attention to what other people are doing and doing the stuff that other people are not doing that needs to be done. And usually the reason why something is not being done when it needs to be is because it's really hard. And therefore it's not going to make any money anytime soon. And it's also not going to, get nice high-profile publications that get people promoted and get their next grant application funded and so on. So that it's also, contraindicated in academia. So because we are independent and we're funded only by philanthropy, pretty much, means we can step into that breach, and we do. So right now, well, there's a whole bunch of things happening. So let's see. Well, there's one project that we've been doing since nearly 15 years now, which we are way ahead of where anybody else could possibly have expected anybody to get, but we've still got a long way to go. And I should mention this project because it started in Australia.
Really?
Yeah.
Nice.
So in the 1980s, a guy in Melbourne named Phil Nagley, who was a protege of another very prominent scientist named Tony Linnane, who's dead now. Phil basically decided, well, what we're going to do is we're going to take bits of the mitochondrial DNA, the DNA from this one part of the cell that has its own DNA, and we're going to put copies of it into the nucleus, into the regular chromosomes, and get it working. We're going to just do some modifications so that it ought to the protein that is encoded by this gene will be able to come back into the mitochondria. And he did this in yeast, very simple organism, but he got it to work for one gene really easily, like in 2 years, which is no time at all in biology, right? That was back in the 1980s. And everyone got really excited, especially very quickly people realized that there could be medical benefits. This was just done for exploratory, curiosity purposes at first. But people realized, well, whoa, if you can do this, you might be able to treat some diseases of the mitochondrial DNA. And some people started to realize that the contribution of mitochondrial mutations to aging might also be really important. And actually, the first person who realised that was also Australian. Well, actually, he was Dutch, but he was working at the University of Queensland in Brisbane. Australia had a distinguished heritage in this department. But here's the thing that happened. People, around about 91, 92, they started to find that it wasn't so easy. That the initial result was a bit of a false dawn, and that there were loads of reasons why this was hard. And everyone just gave up. For the reasons I'm saying, the short-termism that academia imposes. So I came along maybe 6 or 8 years after that and looked at everything that had been published, and I thought, well, this won't bloody do. People have given up too easily. And after a while, when I got some money in the door, I thought, well, okay, let's actually, kickstart, reboot this whole thing. It was a big breakthrough made by a group in France in the mid-2000s, which was a big boost to all of this, but it's just one step in it, really. Long and short of it is, we are killing this one. We are going to make it work. And it's very important because nobody else is working on it, and it's probably going to kill you if nothing else does. And that's not good, really. That's one thing we're doing. Then, we've got other projects that we keep coming up with, of course, that are kind of have some credibility in the sense that they are kind of within a general theme that other people are already happy with, but there is some detail that's difficult, that makes people just neglect it. So, for example, stem cell therapies. Okay, that's a very traditional field, so traditional, in fact, that for the longest time we never did anything in stem cell therapy because everyone else was doing it, and our finances would be a drop in the ocean.
Have you had any stem cell therapy, just quickly?
We are now. So, so this one big thing that we're doing now, and we're doing this at a group at a university in New York, is stem cell therapy for Alzheimer's disease. Now, the big difficulty here is that in Alzheimer's disease, when cells start to die, which is a relatively late event, but still, definitely, potentially recoverable, they die all over the brain. I mean, there are preferential areas, but basically they die all over the brain. And that turns out to be a huge difficulty because if you inject stem cells into the circulation, into the blood, they'll go everywhere, fine. The blood goes everywhere, fine. In the brain, it's not like that. There's this kind of counterpart of the blood called the cerebrospinal fluid, and it's viscous, very viscous. So it kind of sort of flows, but not really. And so if you inject a bunch of stem cells into it, then they just sit there. They don't migrate. They don't diffuse around the way that they do if you really inject them into the blood. And that means they don't get to where they're needed, right? We're working on a somewhat elaborate way to fix this that involves essentially making the cells a bit schizophrenic, making them have one particular type of behavior at first and then switching them into a different type of behavior. This is a completely new idea. Nobody else is doing it, so that's why we're doing it. You get the idea. We do things this way. Another thing that we are already starting to do is combining things. So in academia, there's an enormous amount of balkanization. People will, essentially the best, because there's never nearly enough money for grants, right? So you get a tiny proportion of your grant applications are actually successful. The best way to combat that, to get your grant funded, is to apply to do something that's already smack in the middle of what you're already known to be good at. As opposed to something that's on the periphery of your expertise that might actually be more interesting, right, and more important. So this enormously militates against cross-disciplinary work that actually combines things that have never been combined before, right? And it turns out that aging, it's the ultimate scenario in which cross-disciplinary work is utterly vital. And it's just not done. None of it. I mean, almost none. And it's worse in industry, because in industry, of course, everyone wants to make money and they've got their particular intellectual property, their particular patents, so they work on that stuff and nothing else. And eventually they might get around to, cross-licensing and stuff, but it takes fucking forever. So so we have to step into that breach too. And that's what we're doing. We are identifying cases where you've got things that already seem to work individually a little bit, and we combine them and we see what happens. And we're just starting that. I'm pretty sure, though this is provisional at this point, that combining stuff is going to become an increasingly dominant theme of how we spend our money at SENS, because it's so difficult to justify for other people, and therefore it's going to be neglected otherwise. It's so important. Yeah. And now we're going to have so much more money because of this insane airdrop thing,
That's what I was going to ask you. I was going to say, like, what are you going to do now that you have all of this money? Is that you can do it all?
I mean, right. So, I mean, of course, in a normal world, you'd kind of know what your income trajectory is going to be for the next few years, right? So you'd kind of have plans. I've never had that. We've never had that because about probably 2/3 or so of our income has always been from high net worth individuals. And that is very stochastic. It just happens when it happens, right? And so you can't really plan ahead. You can't. You just got to respond. You got to react. I wish I had been able to square that circle and get the grassroots funding, the small funding from large numbers of donors to ramp up and become a majority of our funding. But we've never been able to do that. It's good, but it's not that good. It's probably a quarter or a third of our funding, so it's very much. Anyone who's listening who is not a billionaire, hello, yes, it's okay to write us $10. That's okay because we do. That it's not nothing at all. We just have to be good at reacting, and so that's what we're doing right now. I mean, this is literally 5 days old, this airdrop thing, right? And so. We're going to have plans within a month, and I've kind of got proto plans in my head right now, but that's all.
Yeah, I bet. So what is the goal at the moment? Are you, in terms of all the stuff that you're working on and researching, and obviously you're trialing different things, are you just going to have like a syringe where eventually we just get to inject a couple of things in our brains, take a couple of supplements, and then we're all good?
Maybe.
I like that.
So the thing we've got to remember here is this is pioneering technology, and when pioneering technology just about starts to work, it's always insanely clunky, right? So I very much expect that there's going to be this short but important period when the administration of these therapies is going to involve a lot of different things that are nasty. Surgery, things like that. And that, of course, means that, number one, it's going to be really expensive to administer. But number two, this is worse, it's just not going to be something we can do to people who are already at death's door, right? We're only going to be able to do it to people who are relatively robust and able to tolerate surgery. So that's the main reason why it's going to be a short period. There's going to be this immense, indescribable effort to expand the applicability of these therapies to people who are closer to death's door. And that, among other things, will mean that we develop therapies that are less invasive, that are just done with injections. And of course, there will indeed be oral administration in some cases. Of course, we can't remotely guess the details, like how short that period of invasiveness is going to be or anything. But that's going to be the overall trajectory of all of this.
Yeah. What do you think that for people who are interested, just from your opinion, very like broad, easy question, from your opinion, people who are just like, all right, I want to live well, I want to make sure that I age really well, and I don't have any diseases or anything coming up, do I just take my B vitamins? Like, what do you suggest? Because I know you kind of look like, oh, okay, all right, there's something going on here. So, what do you reckon?
Well, everyone's different. Some people are more short-termist than others. Some people live for the moment and all that. But I just feel that's fucking crazy. If you don't want to be really sick and miserable tomorrow, then you probably also don't want to be really sick and miserable 20 years from now either, right? And so you have to actually have a sense of proportion about this. The things that are, it's very, very obvious that the things that are available today that you can do, whether it's lifestyle or diet or supplements or anything, can add at most a year or two to your life. And even that is really stretching it, okay? And I'm talking your healthy life here, because of course, let's remember, and this is something I have to emphasize over and over, every interview and every talk I give, we don't work on longevity, right? Longevity is a side effect of staying healthy. So it's all about a healthy lifespan. So you're just going to get very little. And of course that's better than nothing. Who says it wasn't? But in the meantime, you might want to think about stuff that you might be able to do to improve your probability of benefiting from things that don't yet exist, that you can't do yet, right? Because they don't exist. And that, of course, comes down to little things like writing me a very large check, or working in the right area of biology, or just advocacy. We are increasingly getting to the point where we're actually able to have some kind of conversation and interaction with proper top-level policymakers around the world, because they're beginning to get the message that aging is not this inevitable, universal, natural thing that we just have to live with, and that we might actually be able to do something about it, and that the first thing they should think when they think about that possibility is not, oh, fuck, how will we pay the pensions, but rather, it would be quite nice for people not to get sick when they get old.
So what do you think, but personally, do you think are the main breakthroughs that you guys have learned?
That we've learned so far?
Yeah.
Well, yeah, so there's a particular slide that I use in my canonical talk, my normal talk, which lists 4 of our publications. So we've had lots of publications that we've put out over the years, but I list these particular 4 because they are really groundbreaking ones. They were cases where we were able to show that something was, if not exactly possible, at least much more plausible than everybody in the expert community had thought it was. And that really was what got us going. So, for example, I already talked about mitochondrial mutations because it has such a distinguished heritage in Australia. So in, 2016, we were able to report a really important breakthrough. We had another paper last year doing a further big breakthrough. One thing that really helps us, because we're not in regular mainstream academia, is there's this concept that goes under the heading publish or perish. What it basically means is, unless you get papers out there in high-profile journals every 10 minutes, you will not get your next grant application funded, you will not get tenure and all that. We just don't have that. So we absolutely publish, but we publish when we're ready. And we do not decide what to work on the basis of the need to publish. Because we don't have to. We have philanthropic support which believes in us. So that's the kind of thing we've got. There's a few breakthroughs like that. Most of them actually have already led to spin-out companies. This is actually an important point for any of the audience you have who are in the private sector. So our business model used to be, work on the hard stuff and just get on with it. And then, about 6 years ago, just very slowly, but then growing and exponentially growing now, the private sector emerged. People who actually wanted to come in as an early stage, angel investors, seed investors who wanted to actually get properly involved in things that they realized could eventually make serious money. That's the nature of a high-risk, high-reward investor, is they get in really early, right? And, of course, they would come to me because I'm just, I've been around a long time, and if you're a newcomer to this field and you realize that you don't know anything, I'm the top Google hit, right? So I've been able, it's very gratifying because I am the least entrepreneurial person you'll ever meet, but just because I have the best network, and so on, the best expertise, it means that I'm able to actually have an enormous influence in the private sector as well. All right, that's really changed things a lot. And I spend at least as much of my time interfacing with the private sector now as I do within the nonprofit.
Which is crazy. God, I love that. Where do you find...
And of course, I'm not the only one. Let me interrupt for a second. I'm not the only one. So, there's probably 6 people in this field who are the real thought leaders, the people who not only are experts, but also they actually take the time to get out there and do podcasts and lectures and so on to the wider world. One of them, of course, is David Sinclair, who is Australian originally, though he's been a professor at Harvard for a long time now. And we're all great friends. There's only half a dozen of us, really. So yeah, David is very much an entrepreneur. I mean, he and I have a lot in common. We're both very iconoclastic. He's iconoclastic because he grew up in Australia. I'm iconoclastic because I went to the same school as the people who run the UK. And so I know exactly how unintelligent they actually are. But yeah, we're poles apart in other ways. I have always felt that having kids is the most crazy thing to do if you actually want to make a difference to the world, because it's extraordinarily time consuming and lots of other people are very good at it already, whereas David, bless his heart, has chosen to have 3 of them. But the main thing that distinguishes the two of us now is he's really entrepreneurial, and I'm the exact polar opposite of that. So he's doing fantastic work right now, making a huge difference.
Yeah, which is really interesting. However, you said you're not entrepreneurial, but you've been gifted with with all of this funding for the business anyway.
But the point is, it's non-profit funding. I can spend it how I like, and I don't have to.
Yeah, which is exactly right, and you get to spend it how you like on the research that you really want to do. Yeah, and the projects that you're working on.
People just trust me. They trust my judgment on this.
For sure.
And that's true on the for-profit side as well. You have to trust the founders of a company in order to invest in them. So, whether it's at David's end of the spectrum or at mine, it's still you have to be not a bullshitter.
Yeah, for sure. I agree with that. So what results do you think are really good results that are coming out of your lab at the moment that you find could really make an impact to humanity?
So the previous question you had was what are the results that have already come out? And that's an easy thing to say because I can actually talk about the past.
Okay.
The thing about the future is it's very hard to predict.
Yeah.
And especially in science. Einstein had this wonderful quote. He said, if we knew what we were doing, it wouldn't be called research.
Like that.
Einstein had a bunch of really good quotes, and that's one of my favorites. But yeah, so of course I had no idea. But that's okay. Because, first of all, we're doing a lot of different things. And second of all, it's not just us. There's labs all over the world, and we're talking to each other all the time. This is one of the most amazing things about this field, is that it's so collaborative. And this is probably because it's growing so fast, that the investors, the people who are looking to actually make money, ostensibly they are competing with each other. But they don't behave that way, because they understand that at this point, a rising tide floats all boats. And therefore, the right thing to do is to share information and to seek out collaborations far more than you would in an industry that had reached a kind of plateau. So basically, this is just a long-winded way of saying I totally can't answer your question. The number of the breakthroughs that are being made, they're happening every week, every month. Really important things that are happening, and each of them, when I look at it, being focused on the early stage of the science, the things that excite me the most are typically things which are so esoteric because they're early stage that I would have to engage in half an hour of background. I'd have to engage in at least 10 minutes of background, even to a biologist, right? Just to explain why they're interesting at all, right? So I don't really want to go there. But trust me, it's accelerating. I feel just so privileged to be one of the people at the absolute forefront of all of this, to be actually making a huge difference to saving lives. Incalculable numbers of lives that are being saved just by the work that we're doing today.
Mind-boggling. So what can we expect?
Well, okay. So I guess I can't say I can't answer twice in a row, right?
Yeah.
Let me try a little harder this time.
Yeah.
So most of what I tend to focus on when I talk about the relatively near future, but not the immediate future, is longevity escape velocity. So let me briefly explain what that is, because I'm sure quite a lot of your audience won't know. So this is a term that I coined a long time ago, nearly 20 years ago. Very simple concept. The thing is that what we're developing here are rejuvenation therapies, therapies that repair the damage that the body does to itself throughout life and that eventually makes us sick. So what we're doing is we're genuinely taking people at a given biological age, in other words, a given amount of damage that their body contains, and eliminating a bunch of that damage so that we take them back to a younger biological age. Now, the key thing that really means is not just that they've got a bunch more lease of life, but it also means that we're buying ourselves time, us the scientists. So, let's put this into concrete numerical terms. So if someone's age 60, okay, so they're not yet sick, typically, but they're not far away from starting to get the chronic conditions of late life. And these people, right, you might be able to give them this therapy that's fairly good, but by no means perfect, right, that repairs a bunch of the damage in their body, but not all of it. And so those people might end up, after you've done this therapy, they might end up being biologically 30 or 40, right? But then they're going to carry on getting older again. And they're going to carry on getting... Now, of course, you can apply the therapies repeatedly, as often as you like. But here's the thing. Damage is kind of additive. In other words, this difficult damage that the therapies do not repair is going to be also carrying on accumulating. And eventually, however often you apply these therapies, the person's going to get back to having the same amount of damage as what they had when they were 60. And it's all going to be difficult damage. So the therapies are just not going to work, right? So they're going to carry on getting older and sicker and die. And that's not good, really. But the thing is that that's not going to happen until they're like 90. And that means that people like me have had 30 years to improve the therapies so that we can repair the difficult damage. Probably not all the difficult damage, but some of it. And that's good enough, right? So we give the, rejuvenation 2.0 to these people when they are 90. And it will work. We will be re-rejuvenating the same people so that they won't be biologically 60 for the third time until they're 150 or whatever, right? And so on. So it's just a case of keeping one step ahead of the problem. And if you look closely at what this means, in terms of plausibility and everything, essentially it means that once we've got there at all, once we've just about got to the point where we are keeping pace, game over. It's going to get easier over that thereafter. And there's no way in hell that we're ever going to fall back and things are just going to not work anymore. So one of my friends coined the term the Methuselarity, which is like the singularity, right? But this is the point at which we reach this stage called longevity escape velocity, where we are improving the therapy faster than time is passing. So, of course, the big question is, how soon are we going to get to the Methuselarity, right? And, of course, we haven't the face idea. This is pioneering technology, right? So, of course, it's massively subjective and speculative, anything that someone says. But I nevertheless feel I have to give a prediction, because however speculative and subjective my prediction is, it's better than yours. It's better than, right? So I think that it's about 15 years. I think we've got a 50% chance of getting there within about 15 years. Now, to put some perspective on how speculative that guess is, I want to say that there's at least a 10% chance that we won't get there for 100 years, right? But who gives a damn? 50%, that's quite enough to be worth fighting for, right?
Oh, for sure.
And that's going to be in time. That would be in time for most people who are alive today, which is, in fact, it's probably going to be in time for most people who are paying taxes today, which is, fairly important.
Yeah, that is absolutely mind-boggling to even think about. And that's direct result of what you guys are doing, which is fantastic. And thank you for sharing that message. What are some of the actual damages, just for people to understand in their mind? What do you think are some of the damages that's really important for people to be aware of that you're literally trying to reverse?
Yeah, so they're actually really simple to describe. I mean, let's not go through all of them, but I'll give you an example or two. So one is loss of cells. So what does that mean? It simply means, of course, sometimes cells die, right? And in most tissues, in most parts of our body, when a cell dies, it just gets replaced by the division of another cell, right? But there are certain situations in which that does not happen, in which the cell dies and it's just not replaced. And so, of course, that means that over time, the number of cells in that particular place goes down. And eventually, there's not enough cells for that organ or tissue to do its job. So, Parkinson's disease, best example, probably simplest example to describe. There's this one teeny tiny part of the brain, it's called the substantia nigra, and it is the home of a bunch of neurons called dopaminergic neurons. Those are special neurons. They make this one chemical called dopamine, and dopamine is a really important chemical in the brain. If you don't have it, then bad stuff happens. And sure enough, when you have lost maybe 3/4 of your dopaminergic neurons, you are screwed. You get Parkinson's disease. In fact, it turns out that dopaminergic neurons die much more rapidly than most neurons, just for complicated biological reasons. So all of us have lost maybe 1/4 of the ones that you've got right now. I've probably got fewer than you have, right? But 1/4 is okay. That's within the margin of the slop of the system, right? So you've got enough dopamine after that. But if you've lost 3/4 of them, you're fucked. So, and of course, everything varies from one person to another, so this is bound to happen. So what's the fix? The fix is obvious. Stem cell therapy, right? You just stick some what are called dopaminergic precursors into the substantia nigra, and they divide and differentiate, and they replace the neurons that the body was not replacing on its own. Now, in case you hadn't noticed, in case you hadn't guessed, it's not actually that simple. But it's fairly simple. It's fairly simple. So actually 30 years ago, people in Sweden tried this. A research group in Sweden actually did a clinical trial. It almost never worked because they were just really completely, it was enormously hit and miss what they were doing. But very occasionally it did work. And when it did work, it worked like unbelievably spectacular. Like people were completely devoid of Parkinsonian symptoms for like more than a decade after one treatment. So that's about as close to a cure as you can get. And because of that, people are now reviving this. So because now we've got a huge amount more knowledge and skills about how to manipulate stem cells in the laboratory before we inject them. So now we can inject the right kind of stem cell reliably. And so sure enough, there's a new clinical trial going on already in Japan. There's a couple more starting in the US. This is a very big deal now. And everyone's very optimistic. That's just one example. Another example, let me think, which one shall I use? I'll use waste products. So, this is a good one actually, because quite important in Alzheimer's disease. Alzheimer's disease, big deal, right? Alzheimer's disease is very bad at killing you. And that, of course, is the main reason why it's such an epidemic globally, because, people they go really badly downhill, they've got no brain left, and they're still alive. Bad news. So the thing about Alzheimer's is there's lots of things that go wrong with the brain at the same time in Alzheimer's. And one of those things is the accumulation of what are called senile plaques. This is kind of a waste product that accumulates not inside cells, but in the spaces between cells. And about 25 years ago, a group in the US figured out a clever way to use the immune system to get rid of this. And they showed that it really worked in mice. But the thing is, mice don't get Alzheimer's functionally. Okay. You can make artificial mice, you can mess with their genes, so they kind of get bits of Alzheimer's. But, and that was basically what was used to demonstrate that this therapy worked. And everyone rushed headlong into clinical trials, too fast actually. The first clinical trial had to be abandoned prematurely because of the side effects. But eventually, people figured it out and they got it to work. So now we have, I'm going to say 4 or 5 different therapies that eliminate this stuff, these amyloid plaques from the brain in Alzheimer's disease, in human beings, not in mice. And one of them just got, like a couple of weeks or a month ago, it was approved by the Food and Drug Administration in the US. problem is, it doesn't work in the normal sense of work. In other words, the people don't get smarter again. At all. I mean, hardly at all. Now, to me, that's no surprise whatsoever, because there's lots of things that go wrong in Alzheimer's disease, and this thing only fixes one of them. So, duh, really. But that's fine. We've got this therapy in our back pocket to combine with other therapies that we're still developing to fix the other bits of Alzheimer's. So, as far as I'm concerned, it's fantastic. But here's a really good thing. And this is actually very important because a lot of people overlook this part, but the industry certainly does not overlook it. Regulation. The Food and Drug Administration is the regulatory body that approves a drug for administration, okay? And that is a gatekeeper, the number one gatekeeper for profit from drugs, which means it's the number one gatekeeper for investment in the development of the drugs in the first place. The FDA did this very, very brave thing. They said, right, we're going to approve this drug, even though it's basically useless, because it gets rid of plaques. In other words, they were happy to say, okay, we're going to just ordain that this thing that happens that's correlated with cognitive decline in Alzheimer's is a sufficiently predictive and causative component of Alzheimer's that if you can get rid of it, then you've got a drug. That was, I cannot overstate how bold that was, how brave that was by the FDA. And I think they're going to have a hard time getting away with it, to be honest. They're being very sharply criticised for it. But it is exactly what was needed, because we are going to see this over and over again over the next few years, cases where we need to just have faith that therapies which fix one part of a problem can eventually be combined with therapies that fix the other part.
So essentially, you're like a puzzle piece, put it together type of person. You get all these different parts of a puzzle, and you're figuring it all out to put them together, and then trying to.
That's right. And let me say one thing about that, because you've put your finger on it there. The thing is, this is antithetical to the way that people who study the biology of aging used to think. When I came along, for the first 8 or 10 years of my time when I was trying to sell this whole damage repair approach, I was considered to be a real heretic. And a lot of people were very angry with me, and they would say that I was being unscientific and all that. This is normal for any really big paradigm shift, but it's a measure of how big a paradigm shift it was. Right. So the past 10 years, it's not been. It's all over. Everyone accepts that this is totally reasonable, and I don't have to justify myself to my colleagues anymore. But I really had to work hard at that. And that kind of goes with the nature of medicine. Medics understand that what they're doing is basically guessing. It's black magic. And so they try to keep things as simple as they can. And the idea of co-administering a bunch of different therapies to the same people at the same time, they run away very fast if they possibly can. This is really something that's going to have to change. And this is the kind of result that's going to change it.
Yeah, I agree. Tell us about a time when you've been working on something in the office with your team, researching, and you guys got a really big win, and what happened with that?
It's interesting, really, because, what happens is nobody else outside of the lab can know that it's a big win. Not just because we want to keep it secret. We never do. Of course, we don't want to keep it secret, but just because it takes so long to explain why it's important. So here's a great example. We have this wonderful junior researcher, well, relatively junior. She's been with us 4 years now, something like that. She started from basically nothing. She's grown from strength to strength. She's one of the most dedicated people. She's a fantastic researcher. And one of her main themes for 4 years has been a particular feature of a particular technical detail of this business of putting the mitochondrial DNA in the nucleus that I mentioned earlier. But it's a really, really vital technical detail. If we can't get this to work, we're screwed as fuck. We cannot. So it was so important. And, I need to put your audience in the mindset of a researcher, right? You never know what's going to work. you have to have the patience of Job, and you have to have the stubbornness and the bloody-mindedness that, it's no words for it. And eventually, if you're lucky and really good, something works. And so this wonderful researcher, Bhavna Dixit, she, about, I'm going to say 5 months ago, she found the answer, the way to break this Gordian knot that she'd been working with for all these years. And it wasn't just a little incremental advance. It was black and white, like we went from being utterly unable to do this particular thing to it just like totally works. And, I was almost in tears because I knew how hard she'd worked and how important this was. There was a lot of celebration.
Yeah. How did it make you feel?
Very proud. Very proud.
Yeah.
That I've brought together. I mean, it's not just the researchers, of course, it's the admin people as well. That I've brought together a team who, are unimprovable. They're just the most extraordinary team.
Yeah. You can sound like modern day Superman, literally just bulletproof with researching.
Well, I mean, we do it together, right? Some of us are more bulletproof than others. But, I went to the same school as Churchill. I think I mentioned that earlier, right? So I'm pretty fucking bulletproof. I give a lot of moral support and, that kind of thing to some of my team who are not quite like me personality-wise.
Yeah, for sure.
But we all play our part.
Yeah, I agree. And I can see that for sure. And thank you for doing that and making everything, revolutionizing all this stuff. What are your thoughts on DNA?
What do you mean?
like what is
like your thoughts about cosmology?
Yeah, well, sort of, because you're so at the forefront and you understand DNA on a level that majority of people will just never get to understand. When you're researching or working on DNA, like what are the thoughts that go through your mind in terms of what do you think about when you're...
Okay, how can I answer this question in a way that makes any sense at all? Let me think.
Yeah.
Well, okay, so perhaps one of the most important parts of how I think about genetics and about how what approaches to modifying our DNA might or might not be useful is I follow an adage that was first articulated, was most eloquently articulated by a Russian biologist back in the 1960s. He said, "Nothing in biology makes sense except in the context of evolution." In other words, if you look at the body and you see that this or that thing seems to be, bad for health in old age, right? But if that thing is regulated, in other words, it is a consequence of the amount of protein that's being made from this or that gene, right? It's genetically encoded, then you've got a problem. You're probably wrong. In other words, what you know is that the genome is doing this thing, the cell is doing this thing for a reason that makes sense to the cell. Now, there are loopholes in that logic, but you have to actually find such a loophole in order to determine that you might actually be doing good by disrupting what the cell is choosing to do.
Ooh.
So, for example, this whole business about putting the mitochondrial DNA in the nucleus, it has been known for a long time, a very long time, like 50 years, that the mitochondrion arose from what was called an endosymbiotic event, where there was a bacterium and it swallowed another bacterium and they became a symbiotic pair. And at the time that happened, the one that was swallowed had probably 1,000 genes. And now it's got 13. Right? So what the fuck? What happened to the others? The answer is most of them moved to the nucleus. They were transferred spontaneously to the nucleus over evolutionary time. but over a relatively short time. So why didn't that whole process run to completion, right?
Yeah.
That's an important question, a really important question. The reason it's important is because if you understand the answer, then you can understand, the various answers you might come up with will enormously determine what strategies for medically moving it to completion might work and which ones might actually be bad for you. And it turns out that, yes, there is indeed a spectrum of opinion about that in the expert community. And the people who are completely wrong are wrong because they didn't think the evolutionary things through. So I had to actually go to the trouble of writing this enormous review paper back in, I'm going to say, 2005, explaining why the people who are wrong are wrong. I should not have had to do that, but I did. And this is not the only time. I used to spend a lot of my time pointing out why people who are wrong are wrong. So that's just one example. But there's plenty of other examples. But also it works the other way. For example, I always am looking for cases where evolution has done the hard work for us.
That's smart.
Where we'd like, for example, let's say there's a waste product that's accumulating in the cell. So I talked earlier about waste products that accumulate outside the cell, like amyloid plaques.
Yep.
That turns out to be relatively easy. You can kind of tweak the immune system. But waste products that accumulate inside the cell are much harder, and for various reasons that I won't go into now. And so I came up with this idea that we would use enzymes that were created in other species, especially bacteria, to break this stuff down. Now, you may ask, what? Why would such enzymes even exist? And that's the lateral thinking. That's thinking in terms of evolution. Turns out there's an entire field that's not even medical. It's actually to do with environmental decontamination. It's called bioremediation. And it's existed, again, for like 50 years. And it revolves around the idea, which was once called the microbial infallibility theory, or something like that, that basically, if something has energy in it, if you can break it down and actually extract energy from it, then bacteria are going to evolve the ability to do that. So it's literally true. If you go to like a disused airfield, right, and it's got like, dioxins or TNT in the soil, and you want to build a housing estate on it, you can't, right? Because it's got this right. So what do? You've got to get rid of the pollutant. How? The answer is you just spray the thing with bacteria that are capable of breaking down TNT and turning it into something completely non-toxic.
And that works.
Yes, it works. It totally works. But the reason it works is because such bacteria exist. So the question is, why do such bacteria exist at all in the first place? And the answer is because TNT has energy in it. So if you can break it down, you can live off it.
So if anything has energy in it,
not anything, but organic molecules, especially toxic organic molecules, do tend to, yes. So we've adopted this, and it's working pretty well for a bunch of things. We're using it against macular degeneration, the major number one cause of blindness in the elderly. One of our spin-out companies doing that. But you can see the lateral thinking is enormously relevant, and a huge amount of that lateral thinking revolves around evolution.
Yeah.
Around thinking the way evolution thinks, putting yourself in the mindset of evolution to anthropomorphize far too much, right? So the reason I chose to give that answer to your question about DNA was because, of course, evolution is all about DNA, right?
Yeah.
You just have to, you have to think, okay, what does natural selection really mean? Kinetically, mechanistically, over time, what's it likely to lead to? And that's the way I think.
Yeah, and I think that's quite fantastic, and I haven't looked at things in that perspective ever. So thank you for sharing that.
And there's plenty of much more high-profile examples. So CRISPR, exactly the same thing. What happened there was a few people were studying this extraordinarily esoteric phenomenon in bacteria, and they suddenly realized, fuck, we can use this medically.
Yeah.
And they've got Nobel Prizes and everything. Here we are, right, in no time at all.
Yeah, and so essentially just to wrap my mind around it, there's DNA, CRISPR reads DNA, but it's also the bacteria in DNA, which then...
Okay, no, you've totally got that wrong. So CRISPR, the best way to describe CRISPR is the adaptive immune system of bacteria. So what happens is, just like we have viruses that, infect us, bacteria have them too. They're normally called phages. And bacteria need to defend themselves against these viruses. And the way they do it, one way they do it, is they incorporate bits of the DNA of the viruses. Once they have fought them off for the first time, by whatever difficult means, if they got lucky and they were able to fight them off, they incorporate bits of the DNA of the virus into their own DNA in a very particular way so that they can recognize it more quickly next time. And that's what CRISPR is. That's the CRISPR process. So the way it's used medically is that we've got essentially this way of adapting the same defense process to edit our own DNA, to use an enzyme called Cas9, which is what's called an exonuclease. It cuts DNA, but it only cuts it exactly where you tell it to. And the way you tell it is is stolen from this bacterial clever thing.
Okay, that makes sense. And by looking at things in the work that you're doing, are you extending telomeres or understanding how telomeres work? How's it working with the...
Okay, I guess I got to talk about telomeres. And this is okay because one of the most important discoveries in telomere research, again, was made in Australia in the mid-90s.
Oh, go to Australia.
Oh yeah, I mean, I am not exaggerating here.
Yeah.
You guys have done really important work. So let me come back to that in a moment. So telomeres. Okay, what are telomeres? Some of your audience probably don't even know that, right? So let me start from the beginning. So telomeres is the name given to the ends of the chromosomes. Chromosomes are, of course, this long chain of DNA, right? It's got ends. These ends, it turns out, are quite important because of two things. First thing that's important is what's called the end replication problem. So DNA, whenever a cell divides, obviously the DNA has to be copied. And it turns out that that's a tricky process that only evolved once, basically. And it didn't evolve very well, such that a linear chromosome, a chromosome with ends, as opposed to a circle, which is what bacteria have, or mitochondria for that matter, a linear chromosome, the ends of the DNA don't get replicated properly. So the chromosome gets a little bit shorter every time the cell divides, which eventually is pretty obviously a bad thing. Right? Now, the other thing is that chromosomes suffer damage all the time. Now, bad shit happens. Oxidative damage, cosmic rays, whatever. And sometimes chromosomes get chopped in half. They actually just break apart. And this happens actually often enough that the cell needs a way to fix it. So the cell has a way to put chromosomes back together again after they have fallen apart. But wait, bit of a problem there. How can the cell tell that two separate chromosomes are not simply two halves of a broken chromosome? Very tricky, right? So by default, what would happen is the two chromosomes will be joined together end to end. And there's a whole bunch of reasons why that's an extremely bad thing for the cell, okay? So the chromosome has to be able to tell the difference between an actual broken chromosome and the end of a real chromosome. And the telomere is how it does it. The telomere consists of this very simple but very distinctive sequence of DNA, which is wrapped around in a rather elaborate structure called a T-loop, and which basically does everything I just said. And if the chromosome gets shorter and shorter, as I just explained with regard to cell division, you've got a problem, because this specialist sequence that is wrapped around in this clever way that that doesn't get joined to another chromosome, that goes away. Eventually, you've got none of that left, and the chromosome does get joined together end to end. It really happens. So something has to fix that, right? Because eventually you're going to have too many cell divisions. And so there's this enzyme. It's called telomerase. And it's responsible for adding additional meaningless but distinctive sequence onto the end of the chromosome to compensate for the failure of DNA replication to do it on its own. Works really well. Except that there are some occasions when we'd rather like cells not to be able to divide indefinitely.
Yeah, like bad ones. Yeah.
What?
Like bad cells, like a cancer cell or something. You don't want that one.
Or something. Exactly.
Yeah.
Cancer cells.
Yeah.
I see cancer cells. Right. Yeah. Cancer is more or less, by definition, it is cells dividing uncontrollably. Right?
Yeah.
And sure enough, given everything I just told you, what this means is that cancers that get into this state where they've got a bunch of mutations where they're not like paying attention to staying quiescent, they're just dividing and dividing and dividing. Once that glob of cells gets to be even a millimeter or two across, it's just gonna vaporize if its telomeres get too short, because this chromosome joining thing that I mentioned, and that sounds great, but unfortunately, what happens is that they have this thing called telomerase, which allows them to escape that problem. Now, the human body is aware of this. And of course, I'm talking, anthropomorphically and teleologically here, right? But the evolution has been aware of this. And so what's happened is that every cell in the body suppresses telomerase as much as possible. There are only a few types of cell in the body that need to divide a hell of a lot, enough that they would need telomerase. In other words, enough that they would get into trouble if they didn't have it, because their chromosomes would get too short. Most cells just don't divide that often in the first place. So it's totally fine to just completely, 100%, absolutely turn off telomerase. And therefore the chromosomes do get shorter on those rare occasions when the cell divides, but that's fine. You can have a few of those divisions. In fact, you can have a few dozen of those divisions before anything bad happens, right? But a few cells have to do it a little bit. Cancers have to do it a hell of a lot in order to get big enough to kill you. So they have to really turn on this one gene, telomerase, and 90% of them do. And so this is a massive, massive thing. If you look at the way that most people talk about cancer, most oncologists talk about cancer, they'll say, well, it's not really right to talk about cancer as one disease because it's a different disease for every single tissue. There's different cell types, and that's true in a way, but it's also not true in another way. Namely, almost all cancers have this one thing in common: they have to turn on this one gene, telomerase. If that didn't happen, if that could not happen, it would be quite good, really.
Yeah.
And so 20 odd years ago, I figured out a way to do that, but it was a very, very elaborate way, and honestly, a very ambitious way. And nobody's really got very close to doing what I suggested back then. But now we've got kind of a version 2.0 of what I suggested, which is looking extremely promising. Essentially, it tricks cells into committing suicide really quickly after they start making a lot of this enzyme telomerase.
So you can pinpoint the cells that are making lots of telomerase. And
you don't quite even do that. What you have, it's better than that. It's better than that.
Oh, wow.
What you do is you have a drug, a small drug, that just goes into every cell in the body, but in cells that are not expressing telomerase, nothing happens. It just gets metabolized, it goes away. But in cells that are expressing telomerase, it gets incorporated into our chromosomes in a way that causes the cell to say, oh, fucking shit, I need to die right now. And this drug was developed by a group in Dallas, in Texas, maybe 10 years ago. It's taken that long to get through to this far. It's now being pursued by a company. It's in clinical trials already, but it's not nearly well enough funded. So any billionaire who's listening right now, this
Fund
is
it.
especially any billionaire who wants to make money, not just to give away money, and there's more of those, right? This is, it is totally on the. I don't like to choose a number one company, but it's on the podium. This is this is unbelievably important. It's the single most important anti-cancer therapy that exists right now, and it's not nearly going fast enough.
You must see this like so regularly, where you've had some new research, people obviously in your network of community, because you guys are all communicating together, where you see all these massive potential either drugs or research or breakthroughs, and just think like, would someone just take it from...
I have the privilege that I have some influence, right? So when I come across something that's absolutely fucking insanely important, I can go to a lot of people. The reason why this clinical trial is happening already at all is because of me, because I, brought money in.
Thank you.
But not nearly enough. Not nearly enough yet. So, write to me. Put my email address in the show notes.
Okay.
Aubrey@SENS.org. Not that my email address is particularly hard to find. I have that way of doing things. But I didn't get to the Australian component of this. So I mentioned that only 90% of human cancers have this mechanism of turning on this enzyme telomerase. What the hell? The other 10% also have the same problem. In other words, they have to maintain their telomeres in order to survive long enough to kill us. And there's another mechanism. And it was discovered by a guy at the University of New South Wales, whose lab is still the leading lab in this space. Honestly, until only a few years ago, he's had more or less no competition, because everybody else felt, oh dear, this is terribly hard. It is terribly hard. It's a challenging research area. And this is, the ultimate testament to what I was saying earlier about the short-termism of academia. Because everyone in the telomere field, everyone across the world, has been aware of this and been tempted to get into it, and they've got into it for about a month. And then they decided, oh, this is far too hard. We won't get publications next week. So they've given up. It makes me spit. But things are better now. There's more labs getting into this properly. But I say it's difficult. So I mentioned that the standard method that 90% of cancers is just one enzyme, telomerase. Easy to characterize, everyone understands more or less everything about it. This other mechanism, it's actually, you can tell from its name that it's not understood. It's called ALT, A-L-T, which stands for Alternative Lengthening of Telomeres. So that says something else. It doesn't say anything more than that, right? Seems like there's probably only one alternative mechanism of lengthening of telomeres, but it kind of depends what you mean by one, because a lot of different genes are involved in a very complex dynamic of kind of controlled chaos that goes on, which is often called replicative stress. And so there's still some way to go to really characterize this to the point where we can actually intervene. This one thing I was telling you about, this drug that kills telomerase positive cells, it would not work on these cells, which is a bit of a shame, but we'll get there.
Yeah. It's just crazy. Absolutely crazy. It's sort of like, I can't believe, like myself, it mind boggles me that you can literally just make a drug. You can make a drug or some sort of method instead, because I was thinking like, hack someone's body open and get in there to order figure this out.
So let me explain how that happens. Because yes, I agree with you. I think most non-biologists, non-scientists would think exactly what you just said. And in fact, to be honest, most scientists would think what you just said. The creativity that's involved in developing and identifying therapies is hugely important. Sometimes it really comes down mostly to trial and error and just blind, high throughput, blunderbussing. But a lot of the time, no. A lot of the time it involves actually doing a bit of, using your brain and using what you know and thinking, what might work? And this is what happened with this drug called Thio that I'm mentioning earlier against telomerase. The group in Dallas, just like Jerry Shea, he just thought, well, okay, supposing there was a sulfur atom there, literally, wouldn't that actually, be quite interesting? And he tried it.
And it worked.
Yeah. So just like, I mean, I cannot overstate how important it is that I have a hot tub. I have a hot tub out there in my yard, right?
Yeah.
And I spend a lot of my time out there. And a huge part of why I spend a lot of my time out there is that that's where I have my best ideas. Just staring at the sky and talking to myself. And, so there's so much too little of that in science, of people being able to actually think.
Yeah, I really like that. Sort of, I read the book Deep Work by Cal Newport, and he talks about and uses a whole lot of examples of how people putting stillness into their lives and allowing time to specifically generate ideas that they can take action on, which may have influence in their work, in their life, in their interpersonal stuff, is so critically important. And I love that you're doing that.
Yeah, thank you for saying that. Specifically the fact that you didn't restrict it to science, because I completely agree. It applies way across the human condition.
Yeah, I find a lot of people who do end up start doing that and asking the big questions and almost introjecting things interpersonally end up going down a path that they really are supposed to be on or want to be on.
Yes.
Yeah. No, I love that. I just want to say before we end up, because I'll give you some time because I know that you're busy saving the world. I just want to say for people who are really interested in anti-aging, in being better and looking after their bodies, if you'd encourage them, like what would you encourage them to start doing now that you think could be beneficial to them, even if it's just learning, whatever it is, because obviously it may not be.
Well, totally. So learning actually is the single most important thing, because the more you know, and I don't just mean about science, I mean about the social context and everything, the reason why people like me believe so deeply that this is the world's most important problem. The more you understand that, the more you will be able to communicate it. And that is critical. So many people think, oh, well, this all costs money, therefore we'll leave it to the billionaires. But that's bullshit. Because the fact is that the poorer you are, the more people you know who are wealthier than you. So it's all about advocacy, really. And, this is not just some kind of, joke that I'm making there. Let me give a sense of this, right? I know for a fact that there are at least 3 really wealthy people in my immediate circle who have never given us money or who gave us a little bit and then stopped. And the number one reason why was because their wives told them not to. So in other words, basically, even visionary people who have money are not an island. It's an ecosystem here. The more that we can persuade enthusiastic people to get more enthusiastic, just that they'll write checks, the better. But equally, the more that we can get unenthusiastic people to be less unenthusiastic, also the better. We need to win this argument. So advocacy is something that everybody can do. You don't have to be a talented biologist. You don't have to be a wealthy individual. You don't have to even be a journalist. I mean, journalists are obviously enormously important, right? Anyone who does a podcast, anyone who writes a column, But so it's all about everyone pulling their weight in whatever way they can.
Yeah, I completely agree. Just quickly as well, what internal work do you do, for yourself to keep yourself sharp? Because you're really enthusiastic.
Thank you. Good question.
You've got really good energy, and I really like that. As soon as you jumped on the podcast today, I just immediately went, I love Aubrey's energy. You just come on, big smile, big talks, we're straight into it. So what do you do to protect your energy?
I don't really do anything. I mean, part of this comes back to what I said some time back, that I had this enormous privilege of having all this adulation all the time, right? People coming to me and doing what I say. I mean, yes, probably I do have natural leadership skills, but the fact is they have worked. There are a lot of people out there who basically just like to do what I tell them to do. And that's, it's very easy to get out of bed for that. It's enormously, fulfilling.
Yeah.
But the other thing is just physiologically, I'm well built. I'm just lucky. I, half a dozen times over the past 20 years, I've had my biological age tested in this or that way, and I always come out way younger than I actually am, like well over a decade younger. So, I don't know, I just had the right nutrition in the womb, things like that. No, I mean, I'm not kidding. That is actually a big contributor to how long people live, to the variation in how long people live. So, yeah, for me, if it ain't broke, don't fix it, more or less. I mean, of course, I do pay close attention to any hint that things might be changing, but as things stand, I'm just living the way I always did. I'm just one of those lucky guys. I can eat and drink more or less what I like and nothing happens, and I don't even need much exercise. I'm not recommending that approach to anybody else. What you need to do is, what works for you.
Yeah, I completely get it. What I also find fantastic, which was fascinating, what you said was privilege. And just a quote from Friedrich Nietzsche, he said, there was a quote that he did say something along the times of, it is a privilege of those who gain strength from owning themselves. Being able to own themselves or being able to command themselves is a privilege of the strong. That's what it was. Those who can command themselves is a privilege of the strong. And I guess you're in a position where you command yourself. You get to command a lot of other people. You have massive responsibility and massive respect. So from my perspective, it seems that you're living for a reason, for something that's greater than yourself, and it is recharging your energy as well as having some really good bulletproof genetics there.
Well, let me actually respond to one word in what you just said, which is the word responsibility. Because that is a word that weighs very heavily with me. Mm-hmm. I've got enormous power now. I've got enormous influence. There are people who would walk through Mordor for me. Lots of them, right? And I feel that every day.
Yeah.
So, I mean, with great power does come great responsibility, and I am that. I have hard days, when bad things happen. And a lot of what powers me through those days is the knowledge that I owe it to the people whom I've brought together.
Yeah, I can see that. And that's where you get really, that's where you find meaning and get fulfillment.
Oh, fuck meaning. I don't do meaning.
Oh, okay.
I don't do that.
Okay. Well, yeah. Well, I guess it's just that responsibility is what, would weigh really strong. Yeah. And I love that. So, yeah, a huge thank you. Aubrey, I'm proud of you.
Oh, thank you. Thank you for having me on the show. I'm always pleased to speak, especially to a podcast that I've never done before, because I'll reach new people and all that. I mean, one thing that blows my mind all the time is the unbelievable number of people who just don't know about this. Yeah. I mean, what the fuck? Why have I been out there doing all this media since fucking 2003? How did people, what rocks have they been hiding under? But I kind of don't care if they're on board now, right?
Yeah, so true. And a massive thank you for actually taking the time out of your busy schedule to get on media, to get on Joe Rogan podcast, to get on every other people's podcast, to get up and do the talks, to jump on my podcast.
Let me be clear. I mean, thank you for thanking me, but it's really, enlightened self-interest. I do it because I know that it's a vital component of what this is about. I'm not trained to be a public speaker. I'm only trained to be a scientist. I'm damn good as a scientist. But the fact is, I've always known that I needed to be leveraging everything else I have, all of my personality, whether it's, my charisma or my determination or my aristocratic British accent or my, unmaterialistic appearance.
Yeah.
Leveraging all of that to get people to actually pay attention to what I'm saying, I'm doing.
Using all the tools in your toolbox, and I respect that. Yep. So where can people who are listening who haven't found you yet, where can they find you?
Well, SENS.org, our website is obviously the nexus of all of this. I'm sure you'll put it in the show notes.
We'll do.
Yeah, S for September, E for Elephant, N for November, S for September, no E at the end. It's not SENS in that sense. .org. And so what's there is obviously massive information. It's written for every kind of audience, from experts all the way through to complete novices. And there's lots of news, stuff, where I'm speaking, but also, of course, actual important news, like, for example, what's actually happened. It's not just about what we're doing, but also what the rest of the community is doing. And there's a contact form that you can't find. You can totally ask us any question you like, and we're extremely well behaved at answering those questions. And then, of course, there's a nice big friendly donate button.
Yeah, which encourage everyone to get on there and start doing it.
Especially right now, given the airdrop, which is blowing my mind.
Yeah, I'm super excited for you, Aubrey. I'm so excited for you. So, big thanks for coming on.
Rock and roll. Thank you.